restart the recording, and here we go. All right, so welcome everyone to the fourth session. I think this is the fourth session of Web3 Teacher Training Track. And today we're going to start talking about writing smart contracts in Solidity. So this session is going to be significantly more interactive than the ones previously. If possible, make sure to open up Remix IDE and follow along with the examples as we go through them. So the way that this particular presentation is set up, here, actually, let me go back here and just demonstrate. So we are going through topic 3 here today. The way that this particular presentation is going to work is if you follow along with the website page here, and just take this code here, should be really easy to just copy this and paste it into Remix. Remix is an online IDE. Once it loads, it looks like this. Oh, getting there. All right, so it looks like this. And so you can just go over here and create individual files and paste your contracts in there and follow along. So the presentation is going to go through bits and pieces of this code, so make sure to follow along. If you have questions, don't hesitate to shout them out. All right, so Remix IDE. Everyone good there? Awesome. So let's go through some of the essential syntax of Solidity. First of all, there is a comment that you'll see at the top of most Solidity files, and that just indicates how the contract code is licensed. I assume most of you have seen stuff like this before: MIT licensed, new public license, etc., or unlicensed if it's not released under a license, etc., etc. This is just the standard practice for licensing or indicating a license in Solidity contracts. Then we move on to selecting our Solidity version. When I wrote the material for this course, the latest version of Solidity was 0.8.4. The latest version of Solidity is now 0.8.6. I don't think I will be updating the contents of this course for patch versions, so this last dot, because everything should be completely compatible across patches. So we'll just do the minor versions there is when we'll update the course content. If this type of version selection syntax is new to you, it is the exact same as NPM, if you're familiar with that. So this just means anything greater than and compatible with. So that's how that version selection works. And then we move on to our contract declaration. Now, if you're familiar with Java classes, this is kind of analogous to, not equivalent to, but analogous to. So we have a lot of comparisons that can be easily made between the two, between Solidity contracts and Java classes. And here we have a bunch of different data types. Booleans, unsigned integers that can range from 8 to 256 bits. Addresses, which can be payable. Addresses, obviously Ethereum address, something that you can send money to, or maybe that holds a contract or something like that. You can have byte arrays of varying sizes, strings, mappings, which we saw in the last session. Mappings are like hash maps, hash tables, dictionaries. It's Solidity's version of that associative array type data structure. Enums, contracts, arrays, structs, etc. There are no undefined or null values and no floating point numbers yet. Right. All right, so we have our access modifiers, and these ones are, despite the fact that public and private look similar to ones that you see in Java, they do work a little bit different. And that's where these internal and external functions come into play. So internal functions can only be called by other functions within the contract. External functions cannot. So, for example, a private function could call an internal function, but couldn't call an external function. An external function could call any of these. And external and public are similar in that third parties, like other contracts or other addresses, can call these functions. whereas private and internal ones cannot be called by other contracts. The view modifier means that the contents of a function, the contents of a method, are not going to modify the state of the contract. So after the function call, there's no evidence left on chain that function was called. Like there's no state change that occurs that affects the contract. And then the pure modifier is a little bit stricter than that, indicating that it does not access or modify state. So it is a view function, but it also doesn't even bother reading from storage. So pure functions might be something just like a very simple data transformation, like a mathematical operation, for example. It could be a pure function. And then we have a couple different global values that you'll see as we go through different contracts. Message.sender indicates the address of either the person or contract that initiated the call to this contract that we're currently in. Message.value indicates the amount of ether tokens that are attached to a transaction. Transaction.origin is similar to message.sender, but you should not use transaction.origin quite as much. The difference between sender and origin is that so contracts can call each other, right? Message.sender always points to the last contract, like the one immediately before this current contract in the call chain. Transaction.origin always points to the first one. Although it might seem intuitive to be like, okay, so we're always going to, just say, okay, the first one that called it is going to, for example, if we're writing ERC20, maybe the first contract is going to be the one that has its balance modified. Maybe they bought more tokens or they transferred tokens or something like that. But almost all the time, it is better practice to use message.sender. That way, a malicious contract can't kind of hijack a call, and because the origin doesn't change, right? So if an innocent, unknowing contract called a malicious contract, and then the malicious contract called another contract that's using transaction.origin, now the malicious contract can almost act as though it is the original contract if the that third contract in the chain was mistakenly using tx.origin instead of message.sender. So it's just better practice to use message.sender. Then we have the require function, which unlike Node.js, where require would like import a module or something like that, require is more like a test assertion. There is also an assert function that operates similarly to require, and we can get into the differences later. But this is like, if the first argument of require is false, it will stop execution and revert all of the changes that have occurred so far. Then we have Kekak. I'm not entirely sure how to pronounce this. 256, that is the hash that Ethereum uses natively. SHA 256. Kekak 256 is a modified version of SHA 256. Both of them are available to you though. Block.timestamp. Important thing to note about block.timestamp is that it is not it's not an exact value. I would say that you could probably trust it to maybe within about a minute, 30 seconds, something like that, but it's not exact. It's not precise. It's only there for reference. Block number, on the other hand, that's absolute, that's set in stone. And block hash, for expect. Yes, there's a link here for more if you're interested in more. All right, so let's talk about gas. Now, this is the cost of running code on the blockchain. And when you compile your contract, it is compiled from Solidity code to Ethereum virtual machine bytecode. And this bytecode contains a bunch of operations, different instructions, and each instruction is assigned a fixed value, a fixed cost, I suppose you could say, in gas. So gas is it's just assigned, it's an assigned cost to each instruction in your bytecode. A regular Ethereum transfer, for example, costs about 21,000 gas. And then gas is converted to Ethereum, and you pay for essentially the complexity or the number of instructions in whatever transaction you're trying to execute in the conversion to gas, or the conversion from gas to Ethereum. So then you pay in Ethereum tokens. So, for example, if the gas price is 66 GWay, which is point, all these zeros, 66 Ethereum, that means that a regular Ethereum transaction that costs 21,000 gas, that means that a regular Ethereum transaction that costs 21,000 gas, you'd multiply that by the price of gas to get the cost to execute that transaction in Ethereum. So then, of course, we can convert this Ethereum price into dollars, and this was taken. This illustration was, I grabbed this. This is a real transaction conversion that I just pulled off of random blocks sometime a month ago or so. So that's when Ethereum was $2,700. So it was a little bit higher. And gas price was really high. Right now gas is, 30 GWay or something? So it's a little bit higher than you'd see right now, but it's a real life example. Right. So, of course, since you're paying for all of the operations that you're executing, you kind of want to keep your gas usage as low as possible, meaning you can follow a couple of these guidelines. Only compute what you absolutely have to, so don't do extraneous computations when you could optimize it further. Storage input-output is very expensive, and memory is slightly less so. So there's a couple different places where your values that you're dealing with in the Ethereum virtual machine are stored. There's storage, and then there's memory. And you could kind of compare this to being like stored on a file in your hard disk versus being a variable stored in RAM. And, that would make sense that reading and writing from a file is more expensive than reading and writing from a variable, right? So be very careful when writing looping or recursive logic, because if you accidentally have an infinite loop, all of a sudden your transaction just got very expensive. And likewise, if your recursive function doesn't have a base case. Right. So let's take a look at some of the exercises in the first section here. Also, we'll probably go till maybe 40 minutes past the hour, and then stop there and do the rest of this topic next time. This topic is kind of intentionally going to take multiple sessions to complete. So let's take a look at some of the exercises we have here. Does everyone have Remix open and have this example code pasted into a file somewhere?
So we can just create a new file and just ignore all the other pre-made files in there?
Right, yep. It doesn't, extra .sol files or whatever, you can just ignore them. They're not going to affect anything. You don't have to delete them or anything. Just create a new one. You can create a folder or something. The file structure is very not important here. So I have, in mine, I have a bunch of different random files in here because I've been playing around in Remix a bunch. So let's see. This is free token. Is this one? There we go. Alright. So, there we go. Alright. So we have this exercise here. Oh. Yes? Sorry, what was that? No? Okay. So we have this first exercise, create a gift function that has this signature. It takes an address and an unsigned 256-bit integer. So create a gift function that adds an amount to anyone's balance and awards the gifter with a single solitary call to the mint function. Couple notes here. Right, so go ahead and do this exercise. It should be fairly straightforward. You can kind of model it as like a combination between transfer and mint, right? So I think just about everything you should need to know in order to create this gift function should be available or should be clear from transfer and mint. Does anyone have questions about this exercise? And if anyone has completed it, let me know. And if you're willing to share it with the class, then you can do that. That would be fabulous. So, yeah, go ahead, write this exercise, and let me know when you're done. All right. Does anyone have an example, or has anyone finished the exercise?
I have something.
Awesome.
Should I just paste it in?
You can share your screen if you're okay with that. Does that work for you?
Yep, sure. Sorry. Sure. So I have a gift function. I marked it external. And then I use the transfer method and pass the beneficiary and the amount.
Okay.
I don't know if you guys can see that.
Awesome. And then we also wanted a complementary call to the mint function in there somewhere.
Right. Oh, I gotta get to that. Requirement is to That it?
All right. Looks good. Right. So there's just one thing, and that is we don't need the this keyword, but otherwise that looks good.
Yeah, I removed it. It won't compile. So I compile it again. Get a bunch of exceptions. So that's how I had it without the this.
Oh, right.
Yeah.
Okay. So this is interesting because we actually remember what we mentioned about the external modifier. It has a very interesting property that actually makes the mint function inaccessible internally.
Yeah.
Right. So
same thing with the transfer.
Same thing with the transfer.
Yeah.
So let's see. One thing to note is that the gift function, we just want to add an arbitrary amount to anyone's balance. It doesn't necessarily need to transfer it, so we don't need the transfer call. Just go ahead and straight away add it out of nowhere.
Just change the balance?
Yep, just directly change the balance. This is a free token, so we can just give it out willy-nilly.
Alright, so this one like this, just amount.
And then add it to the beneficiary. Perfect. And then in order to call the mint function, we have to change the modifier on the mint function in order to allow us to call it internally.
So what do we change? Internal?
We can change it to public.
Public. Alright, that works.
Awesome. Perfect. Yep. So that's absolutely perfect. Awesome. Great. Did anyone else have questions about this exercise? Something that they would like to share?
You can copy over the checks, right? Requires.
Yeah, that works too. We don't need to bother checking the balance of anyone because we're just pulling tokens out of thin air. But that's perfect. All right, great job, awesome. Thank you. All right. Did anyone else have any questions or anything that they would like to? You are still sharing your screen, by the way.
Yeah, I had a quick question about our use of the mint function. So if the mint only increments the balance and multiply by 1, shouldn't we just copy and paste the code but change that to amount?
Oh, that's right. Yeah, we also have to update the total supply. Mm-hmm. Yeah. So, yeah, also update the total supply. Good catch. Thank you. All right. Perfect. All right. So I will resume sharing. Perfect. And let's move on to the second exercise here. So we were talking about gas and efficiency, and it turns out that the transfer function that we have here, it can be improved, and I have the answer right down here, so I don't want to share that. So this function can be improved in two ways. Okay, at least in my testing, I was able to, just using the stuff that we've mentioned so far, get it down from using 28,000 gas to using 12,000 gas, using two optimizations. So the first involves reading from storage. We're reading from storage too many times, reading from storage too frequently. So we can reduce the number of times we read from storage in this particular method here. And then the second one is a little more complicated. And if you read through the material beforehand, then you would have a chance to read through these hints and read through the sample code here and understand what I mean by integer overflow safeguards. So did anyone read through the material beforehand and have an answer to this exercise? Because this one would take a little bit longer. Anyone? Okay, so just...
I have an idea for the first one, but not the second one.
Sure. What's that?
So if we created a local variable at the start called like balance of sender that takes the balance of the message.sender and used that instead of reading to the storage multiple times, that would save us cost, right?
Yep, because it turns out that this right here actually reads this value from storage again. So that is exactly right. That is one of the optimizations. So we can create a local variable called like balance of sender or something like that, replace this with it, and then change this line to say balances of message.sender equals that local variable minus underscore amount. So that is definitely one of them. And the other one involves integer overflow safeguards. It turns out that these requires here actually give us enough sufficient invariance that we can bypass some of the math safety features that Solidity has implemented, specifically when dealing with, for example, unsigned integers, such that when we subtract from them, Solidity doesn't like overflows, but we can tell it to ignore the possibility of overflows, and that'll save us a little bit of gas. So what that would look like altogether is this bit right here, and let me actually zoom in so hopefully people... Oh wow, code isn't zooming. That's annoying. Can people see this okay?
I think you could zoom out a little bit more, expand it a little more. Yeah, keep doing that. Keep doing. Oh,
it's like the code font size stays the same though. I'm not sure what's going on. That's strange. Anyways, what can I do here?
Are you using Chrome? You just use the plus sign on the top. So that seems to work for me.
Oh, here we go. Yeah, sure enough. All right. Here we go. Yeah, I didn't see that. Okay. So here is the solution. That is to, right here, read the balance from, was that Lincoln who mentioned that? Suggested that? So that is exactly right. Read out the balance from the balances here, check it here, and then here in this unchecked block, that removes the mathematic overflow safeguards. So then this line will not have, well, actually underflow. It will not have underflow checks, and that will save us a little bit of gas too. And in my testing, I was able to get it down from 28,000 gas to about 12,000 gas, which is a big improvement. And I think it was mostly from reducing the amount of times we read from storage.
It's funny because you see that type of code everywhere in ERC20 programs.
Mm-hmm.
Right? That type of transfer. It's
right.
Multiple lookups.
Right. So, well, I mean, if we look at the Open Zeppelin ERC20 right here, they do the exact same thing, right?
Yeah.
So they read the sender balance out of the balances array, and then they check it, and they do this right here. It's the exact same thing. So if you use the Open Zeppelin implementation, then you'll be good.
Yeah.
All right. So we have. Okay, let's go to 45 minutes. Let's see if we can, how far we can get through payable functions in 10 minutes. And then we'll do micro presentations and project. All right, so exercises. Done with that. So let's talk about events. Events is kind of a really interesting, unique feature to in Solidity, and it's kind of like your contract is a perpetual event emitter. So you can add libraries that allow you to like RPC read to the blockchain will allow you to add event listeners to your contracts. So contracts can only emit events, they can't listen for events. But the nice thing about emitting events is that it consumes very little gas, and so you can use them for logging things. You can use them as handles or hooks in a web application to detect particular changes, special changes in the blockchain, etc. So, yes, events. Then we'll talk a little bit about payable functions. So you can send Ether to any address. You just send Ethereum there. It just works. But in the case of smart contracts, you can also write functions, which, your contract lives at a particular address, but you can add some call data to your message call that's to your transaction, where you're sending this Ether over, to have it call a particular function with that Ether attached to it. So like we mentioned before, the value of the Ether appears in the message.value identifier in units of Wei, which is the smallest indivisible unit of Ethereum. 1 ETH is 10 to the 18 Wei. So, yep. Attaching Ethereum to a message call. Now, this is something that we should look at a little bit more in depth here. I don't have those examples. So there are a couple different ways that you can send Ethereum to a function, but this is the currently this is the only way that is recommended. There are 2 other functions, send and transfer, that also allow you to attach Ethereum to a message call, but they have fixed gas allowances, and the gas price of certain operations can actually change. So it's not necessarily entirely recommended that you always that you use the send or transfer functions. Right now, it is recommended that you use the curly brackets syntax because this will allow you to customize the amount of gas, fine-tune it exactly to your needs. And that looks like just adding a comma here. It's very similar to like a JavaScript object, comma, and then say gas, colon, however much gas you're sending along with. Otherwise, this will attach the entire rest of the amount of gas that is available to the function, and if the call doesn't use that much gas, then you'll get that much back, however much back it is. So you can also pay addresses directly. Looks like this, and here's where you put the call data. If we're just paying a address and not trying to call a function, then you don't put anything in the call data. So yeah, send and transfer is somewhat discouraged due to fixed gas allocation. Right, so this is how you just pay an address directly, and this is how you attach either to a message call. Yeah. Perfect. All right, and that's how you change the gas limit. So, all right, so let's do some of the exercises here. Right. So we have this very expensive token. Does anyone want to give me a rundown of how this very expensive token works?
So I'm looking at the code right now, first time, but it looks like price keeps going up.
Mm-hmm. By how much?
By 1 ETH, I think.
So the price of the next token goes up exponentially.
Oh, it's exponential. Okay.
Yeah. So this is exponentiation here. So it's 2 to the power of however many tokens are there times 1 ETH.
Oh, I see that.
So it's a very, very expensive token. Yeah. This is... I wrote these contracts more as a way to demonstrate certain language features rather than having them be particularly useful. So I also needed some distinguishing factors to give them names that weren't just contract 1, contract 2. So that is where that name came from. Yeah, don't use this contract in real life.
You could, it'll go nowhere.
You could, and it has a security vulnerability intentionally written into it for the purposes of demonstration. So really, don't use this contract. Yep. Awesome. So I'm going to, before we look at this, just a reminder because we have a couple new people joining us for the first time today. Make sure to review all 4 of these links here: the syllabus, the calendar, some useful links, and the lesson plan. The lesson plan gives you an idea of what to expect each session. So make sure to read the relevant section of the course material before each session and prepare a topical micro presentation. And then work on your project as is described in the syllabus and at the bottom of each section. We kind of have like status updates, and then here is the schedule of each session. So just a reminder how that is supposed to work. All right, so we have this very expensive token where each time you buy it, the price goes up by a factor of 2. So it just keeps exponentially increasing the price. Right, so let's take a look at a couple things in this contract we haven't seen before. This is how you declare an event.
So Jacob, with that price of that token, theoretically, because it's a UNT 256, would it wrap around?
At some point it would.
It
would attempt to wrap around, but since this is not unchecked, it would probably end up erroring, and it would just cease functioning properly. Right. So again, yet another reason to not use this contract.
Right.
We're going to end up, as exponential numbers keep getting bigger, they're going to overrun bounds of a 256-bit integer. That'll just be a big mess. Yeah. All right. So we have this buy event here. So this is how you declare an event. There are a couple of interesting things going on here. So this is how we declare an event, kind of similar to a data type. There's the name of our event, and an event takes arguments. And there are 2 different major types of arguments. There are indexed and not indexed arguments. So an indexed argument means that it's going to be one that you're going to be able to easily search through the blockchain for it. Kind of like if you're familiar with indices in a database, right? So if something is like a primary key, or if it's indexed or unique or something like that, that's similar to how this keyword works. So you'll be able to query for indexed parameters. So this is really convenient when you're listening for events. from a contract that maybe emits a lot of events and you don't want to read all of them. So you'll be able to filter them. And then this one is not indexed, so that just comes along for the ride. So the reason, for example, that this is indexed is because maybe in your DApp, you're only going to have like one person logged in at a time, right? You'll have your one user that's using your app right now, so you only want to see buy events that maybe they executed or something like that. Perfect. So here is then how you emit an event. So when someone calls this buy function, it costs them an arm and a leg in Ether, and then it will emit this buy event with them as the sender, or with the sender as the buyer field here in the buy event. Total supply here is the index of the token that was just bought, and then the message that value is however much it was bought for. All right. Next, token cost. Perfect. You'll see how this one is a view function because it does not modify any state. This one is a public pure function. Next, token cost, and this one is pure because it is simply a mathematical calculation. That's why that is pure. Then we have this withdraw function where we are calling our... Oh wait, this one? Oh no, maybe it's... Oh, sorry. This is the one that has the security vulnerability. It's the next one. So this withdraw function will attempt to transfer all of the tokens inside of this contract's, or that is stored at this contract's address, so our balance, and we'll transfer it to the owner of the contract. The owner of the contract was established when the contract was constructed. When it was first initialized, we established who the owner is. All right, and then our
Jake, a quick question.
Yep.
Were you multiplying the one ETH? What's the point of that? Yeah, what's the point there to do that? For the decimal places, or is it casting?
So this is the ETH keyword is really nice. It's its definition is right here. It just means one ETH. The ether here is just going to mean 1 times 10 to the 18. Right. So it doesn't have any like units or special types attached to it. It is literally just a keyword that you can attach to the end of a number to multiply it by 10 to the 18.
Oh, so it's like a constant.
Sort of, except it appears in code. It looks like a unit, right?
Right.
So you don't there's no multiplication sign here.
Right.
So you just attach it to a number and it will multiply it by that much. And then we also have very similar set of keywords, work just the same for time. So 1 seconds is 1 minutes is 60, 1 hours is 360, 1 days is whatever that times 24 is, and 1 weeks is whatever 1 days times 7 is. And they're just plain integer numbers. They're just for convenience, really. It's just sugar. All right. So then we call our owner here and attach some ether, and it will send the ether over to our owner. All right. So we have 2 exercises here. One is to create a buyout function, and the second is to rewrite the buyout function. So I'm going to leave these exercises with you guys to do on your own time because we are at 49 minutes past. So we will stop here and return next session to these exercises, and hopefully we'll have some interesting submissions. All right, so next we're going to... So that is the end of the instructional part. Now let's move on to topical micro presentations. Did anyone have a topical micro presentation that they would like to present?
Hi, Jacob. This is my first session as well, but I've been doing another introductory course, and maybe I could speak to ownership of this smart contracts. So like if you don't seal down the ownership, certain contracts can allow other users to, I guess, manipulate the addresses or insert different addresses that cause breaks in smart contracts in the long run. So using like an ownership script, I don't know if I'm using the correct terminology, but using an ownership script and then inheriting that script to lock down ownership to the original contract user.
Right, like using the only owner function modifier?
Yes, exactly, using the only owner.
Yeah, perfect. Yeah, go ahead.
So, I mean, that's really all I know about it. I mean, using the only owner modifier, you can apply it to other smart contracts, and then using inheritance that allows the original smart contract user to only trigger certain events based on their usage of the smart contract, rather than allowing it, people outside to alter the smart contract and possibly break it.
Mm-hmm. Yeah, that's a great paradigm. We're going to go through a couple of design patterns in the third section, or the third piece of section 3. So the very next one is called Design Patterns and Security Consideration. We'll talk a little bit about function modifiers there. And like Hector mentioned, one of the most popular function modifiers is called only owner. And it makes it so that only the owner of the smart contract is able to perform a particular function or call a function or something like that. Yeah, really great thing to bring up. Thank you.
I think Hector, you already just gave your presentation. That was it right there.
Yeah, that's all we need. That's all we need for a presentation.
That was 2 minutes right there.
Oh, okay, perfect.
yeah, that's exactly perfect.
You should do it again.
Yep, that's really all we need. Just find a topic, find something interesting about it. 2 minutes. That's all we need. And remember, the goal in this course is the Web3 teacher training program. So we're not just teaching you how to build dApps, although we will do that. The goal is also to help you prepare material that you can reuse to help explain all of these concepts, all the concepts that you found interesting when you hold a presentation of your own. So, or when you hold a workshop of your own, right? So you're going to have all of these tiny topical micro presentations that you can reuse in your own workshops later. So that is the goal here. So I'd really encourage everyone to just take the time, reading through the material. Like next session, we're probably going to go through design patterns and security considerations, and that'll probably be it, because it's a really interesting, vulnerable function right here that I want to spend a lot of time on, because smart contracts are immutable, and if you deploy one with a security vulnerability, it's out there, and there's not much you can do about it. Because you can't, no take back seats. Your contracts are out there. So we're going to spend a lot of time on that. I would really encourage everyone to take, 20 minutes, read through the code here, and then maybe take a little bit more time, read through the different links here. There's a lot of documentation about this type of thing. Re-entrancy attacks, probably the biggest security consideration that, if your contract is vulnerable to re-entrancy attacks, that is like item number 1 on smart contract auditors, to-do list or checklist is, are you vulnerable to a re-entrancy attack, right? Really big issue if you have re-entrancy. That is not cool. So, take, I don't know however long it'll take, 20 minutes, half an hour, read through the code, go through the example. It's a really cool exercise, because you get to not only see the code, see how this is vulnerable, but you're also going to write an exploit and write a contract that attacks this contract and empties its wallet. That is the exercise. So take 20 minutes, half an hour, however long it's going to take. And last 3 minutes, I guess we'll talk about projects. Has everyone established the topic that they want for their project? That was the assignment for last time. Section 2 here. Project status was just come up with an idea. Come up with an idea for your project. Does everyone have an idea for their project? If not, come up with one ASAP, because before the next session, you should start writing the smart contracts for your project. Okay? And don't hesitate to reach out if you need help. I've written a bunch of different smart contracts. If you need help about events, if you need help sending tokens or testing your contracts, or just the syntax of the language, or if you're not sure where to find good example contracts, well, first of all, check out Open Zeppelin. They have probably anything you could possibly imagine there. But if you're still stuck, don't hesitate to reach out. It's what I'm here for. So start writing the smart contracts for your project. Again, this is ideally something that will become a teaching tool for you when you start workshops of your own. You'll already have a finished app that you have explained to other people. You've explained to other people in this course. You've gone through it multiple times. And so you'll be able to use this as a teaching tool when you return to do your own workshops later.